All right, let's start. All right. Oh, quickly, just for next week, maybe review session for the exam. Would it help? Okay. 1, 2. 1 session or 2 sessions? 4? No, not possible. Well, you tell you what, if I schedule for it and no one show up, I'm gonna change the exam to be harder. How about 2? Okay, I tell you what, I talked to the department, so tentatively Tuesday, Thursday, early afternoon. I'll confirm with you. Would this immediately clash with your exam? After 12? Oh, really? Got to be the morning? So if I say Tuesday, Thursday a.m., not early a.m., maybe at 10, maybe. Oh, if I do it after 12, you'll be okay. Okay, I see. Okay, p.m. Okay. You know what? Wednesday, Thursday, I think it's better to have a 1-day gap. So whatever I talk about in the first one, you can study for that and then come back. Anyway, I'll say Tuesday and Thursday. How about that? I'll record it anyway. Okay, let's now talk about how many of you actually got 3101 and 3311? Oh, really? Not on the same day, right? Oh, yeah, you're lucky. Actually, last semester, they scheduled 3101 and 3311 on the same day. And I made the wrong decision to allow for deferral exam for those people. That made me grade 18 papers last weekend. Anyway, you're lucky. You don't have on the same day. Anyway, okay, plan for today. I will spend hopefully maximum 1 hour, I hope. To finish the whole logic, I'll give you some exercise, to go through everything. For sure, whole logic will be covered in the exam, so that's for sure. And in the remaining maybe 30 minutes to 40 minutes, I will refer you to some slides in section Z about agents. They do talk about some deeper subjects. What I will do instead is to do an example in iPhone Studio together with you so that it will be straightforward for you to follow the slides. I think that will be the best way for you to learn. Okay? Going through all the 49 slides from the other section will be too much for just 1 hour. So I'd rather give you the insight into the subjects. An agent will be covered in the exam. Okay? That's why I want to talk about it. Okay, so let's just go back to Hoare logic. Very quickly, this is how we ended up with. Let me just explain again the intuition for you, and then we'll do exercise, okay? So now this is sequential composition, okay? Basically, S1 and S2, they can be arbitrarily complicated. S1 can contain loops, nested if statements. There's no boundary on how complex S1 and S2 can be. So now, let me just tell you what's the insight into this construct over here. So if you got WP, okay, let me make it smaller. Okay, so you got WP, you got S1, followed by, okay, let me just write it properly. S1, semicolon, which means followed by S2. And then you want to establish some post-condition R. That's how you can think about it. You can think about, you start with some precondition Q, okay? You start with some precondition Q, after which you try to execute S1. After S1, you have some intermediate states over here. Starting from this intermediate state, you try to execute S2. And you're hoping that upon the termination of S2, you're going to establish R, okay? So basically, the R over here is the R over here, okay? So now, what's really tricky about this is about this particular intermediate states. Okay, so informally speaking, you want to make sure this states is enough for S2 to establish R informally. Okay, two things. One, the intermediate states is enough for S2 to establish R. That's number one. Number two, you want to make sure upon the termination of S1, you can really establish this particular intermediate states, okay? upon terminating S1, this can be established. Okay, so now the question really is, what should this intermediate state be, right? Basically, we learned about weakest precondition. The weakest precondition for you to start in S2, to execute S2 and establish R, will be the WP for S2 to establish R. So that's the intermediate states. And we want to make sure upon executing S1 and terminates, we can establish this particular WP. So we can think about over here, this is the intermediate postcondition. Okay, there's an intermediate postcondition over here. So that means, so now we want to think about what's the weakest precondition in order for S1 to establish this particular postcondition. Well, how do we write it? That would be the answer for that, right? So first of all, we calculate the WP for S2 to establish R. So that's the intermediate postcondition for S1 to establish. And what would be the weakest precondition for S1 to establish that, right? That would be just another WP. WP for S1 to establish that green intermediate weakest precondition. Okay, that's kind of the insight into why this rule is the case. Okay, because that one somehow it looks a bit funny because you turn one WP into two WP, but that's okay. You just want to phase them into different phases, one after the other. We'll do an example. Don't worry. Any questions? Yeah. Say it again. S1. No, think it this way. Okay, so we treat S1 and S2 somehow independently. Okay, you want to say that we want S1 to establish this whole predicates. Okay, and this predicate here is handling to make sure S2, when taking over the control from S1, can establish R. Okay. Okay, let me say this, but this might be a little bit confusing when you think of it. Okay, but what is the weakest precondition for S1 to establish the weakest precondition for S2 to establish R? That's how you read it, right? But you really want to see the diagram and see the insight, okay? Okay, that's about the rule. So I would say we go back here. Okay, that's a rule. And you can simply, that's the exactly what I said. You can think about first phase and second phase. And now let's try to, okay, so now if you want to prove that, so let's bring the precondition also into play, right? If you're saying that this is the precondition I have, so what will be considered as correct? You want to make sure Q over here is no weaker than whatever weakest precondition we calculate, right? That's what you will see in the slides. Okay, okay, like that. Okay, any questions? So far, just about the rule. And we'll do one example together. Okay? The example would be this. Is this program correct? By the way, what's this program doing? Can you see that? Swap, right? Even if you think that's correct in the exam, you still got to show the proof. Okay? Just for this one, it's very easy. But this one shows quite nicely how you can use the WP rule. Okay, we're going to do it together with you in the beginning steps. Okay, so now you can see that how many phases do we have for this program? 3 phases, right? Okay, so we're going to somehow calculate WP backwards. Okay, exactly how we did it. Okay, so what I would do is I will go for, okay, that's exactly the same. Okay, so there are 2 steps over here. Step number 1, calculate the WP for this program here. I'm going to say the temp is assigned to X, followed by X is assigned to Y, followed by Y is assigned to temp. And we want to make sure at the end, we're going to establish the post condition over here. That's the first step. Okay? Eventually, second step, okay, we're going to do all the calculation. Whatever WP you calculate, you want to make sure true which is the original precondition here, implies whatever we calculate, which we're going to do right now. Okay? So now, help me out over here. You can think about over here, you can think about this is like a S1, and this is the rest. That's how you can think of it. One way to think of it is S1 is a simple assignment, S2 is basically just another sequential composition. So now, how do we apply the rule? Okay, so I'm going to say WP rule for, you can say semicolon, or you can say sequential composition. Okay, either way. Okay, so now what do we have? WP, right? Okay, how about I write down the first one for you and see if you're convinced. Okay, so now what I will do is, basically, I'm just going to calculate, first of all, this part over here, right? That's the phase 2. Okay? Calculate the WP for the remaining phase, except for the first phase. XY, semicolon, Y is assigned to temp. Okay? And then for that to establish the post condition over here. Okay? And then we have this remaining phase over the first phase over here. So that'll be the WP for the temp. Okay, any question until now? Yes, go ahead. Sorry, we're going to do it again for sure. Yeah. You can see that the good thing about making such step is you can see over here we are almost ready to do substitution for the assignments, right? However, this part, we're not ready yet. We're going to split it up further. Okay? So let's try that quickly. So now let me use a different color. Let's say green. So now we want to basically think about this is like a S1 right now. And this part here is like a S2. And then we're going to consider what's the WP for this intermediate step, right? Okay, let's try that. It's going to be, okay. Now we're going to say it's equal to WP rule for sequential composition. Okay, so now this one first. For S2 to establish this, so we're going to get the WP for S2 to establish x larger than y. Okay, and now we want to know what is the weakest precondition for S1 to establish that, right? So it's going to be the WP for S1 to establish this, orange. And don't forget the original one. We want to make sure the first phase can establish such intermediate states. Okay? So we got WP for temp is assigned to x, like that. Let me just say one more thing, okay, before we try to do the substitution. Okay? Oh, you know what? I shouldn't say S1 and S2, right? Let me just put exactly what it should be. This one should be x is assigned to y, and this part here should be y is assigned to temp. Okay? So now you can think about this. What we are really trying to do is like this. This is the eventual post condition we would like to establish for y is assigned to temp to establish, right? In this particular intermediate states, we calculate the WP for y is assigned to temp to establish x larger than y. That's this particular intermediate states. Agree? And then we want to make sure upon the termination for the second phase, we can establish that. So that's why we go backwards. We got another one here. So that would be, for this particular intermediate states, we want to make sure that's going to be the WP for this guy here. X is assigned to y. And then I will simply just copy this part here, right? I'll just say green over here. Okay, follow? Okay. Guys, any questions? If I'm going too fast, please ask questions. Okay, now what should we do? Substitution, right? Basically, you can see that what we have done, you can see the first WP, we are ready to do assignment substitution. For the second WP, we are also ready. For the third one, we are also ready. Okay, it's very useful. Even though we go from the beginning only one WP into 3 WP, that's okay. But at least we are now ready. Okay, let's do quickly. So now, if I try to, which WP should I do first? The inner one, right? Okay, so now it's going to be, okay, let me just write down quickly. WP over here. So this part I cannot do just yet. I'll just copy that. And also for this part I cannot do just yet. Now what about the green? What should that be? Replace every occurrence of y by temp. Agree? That will be x larger than temp. Okay? Any questions until now? Okay, let's do another one. If you want to do another one, how about this? Yes, absolutely, I forgot. Okay, yeah, I'm just trying to give you just enough idea. Of course, oops. You definitely have to do that. So you would say WP for assignments. Okay, so now can we just do another one? So now we should really handle this one here, right? Okay, so what we will get is WP for assignments over here. So we get WP temp is assigned to x. And now what about the orange part? Right? Basically, you're going to replace every occurrence of x by y. So that will be y larger than temp. It's actually not hard. You just have to make sure you don't lose the track. Okay, that's the main thing. So that's why I'm trying to do that together with you once. Okay, after this, you can see that we're almost done, right? Okay, so this will be equal to, again, one more. Okay, WP rule for assignments over here. So you get temp is assigned to x. Okay, every occurrence of temp is assigned to x. So y larger than x. Okay, that's exactly what we have. That is the weakest precondition. I tell you what, if you think about it intuitively, it makes sense. We want the post condition to be x larger than y. And we know that all the program does is to swap x and y. Of course, in the weakest precondition is such that the relation is reversed. Okay? So now this is what we calculated from the first step, y larger than x. So now what about second step? Does true imply y larger than x? Does it? No, it doesn't, right? Because true means any value will be okay. But now we are saying that the weakest precondition tells us only if y is strictly larger than x. Okay? Give me one counter example. Yeah, for example, counter example. Let's say y is 1, x is 2. Yeah? In that case, if you swap them, you wouldn't have that post condition, right? Okay, so is the program correct? No. How do you prove it? Number one, calculate the weakest precondition. Number two, try to argue whether the original post condition implies the weakest precondition. Okay, either prove or disapprove. Yes, if you want to disapprove it, just give a counter example, yes. Yeah. So, so I just don't have space. So first of all, you got to say true implies the weakest precondition we calculated, and then you will say no, it's not the case because, for example, if y is 1, x is 2, you don't have that, right? Any questions? I have one question for you. This is a swap, right? Let's say we still got this, right? We know that actually, you know what? We know that the weakest precondition for a swap intuitively should be y larger than x. And then the post condition should be, let's say it's x larger than y, right? Let's say that. Now, I'll give you a little bit challenge, okay? Can you do the swap without introducing an intermediate variable? Basically, I don't want to use any temp. Oh, no, I don't need any cell. I just want to encourage you to try this. Number one, try your implementation. Number two, prove it. This is an interview questions I heard from my students last semester when they went to an interview. Do the swap between x and y without using any intermediate value. Okay, how about you think about this? Don't tell me your solution. If you really want to know my solution, I'll tell you in the review session next week. How about that? Think about it. Huh? Nothing to do with, you know, I tell you what, even think about it like a Java or C question. I'm just saying, I want to swap between x and y. I don't want any intermediate variable. Okay? Think about it. It's a challenge. Okay? It's a nice application for this technique. If you do have that solution there, you can use the whole logic to prove it. Okay? Okay, think about it. Okay, otherwise, the proof is exactly here. Okay, again, this will be what you have to follow in the exam so that it's easier for us to judge whether your proof is valid or not. Okay, it's really important. Any question about this proof over here? Okay, good. Okay, let's now talk about loops. Okay, quickly. Well, you definitely have to use the loops so far. Okay, if you use the across loops, you don't have to worry about the subject we're going to talk about now, because across loop, you definitely got termination, no problem. You always make sure you iterate through the collection for exactly that many of times. However, if you try to use a from until loop, which can also be easily translated into Java or C, you have to worry about termination and other correctness issue. So let's talk about it quickly. Okay, so how many of you have not heard about loopy variance previously? Have not? Every one of you have heard about it? Really? That's good. 3101? Okay. 2001? Why would you learn about loopy variance in 2001? Oh, yeah. Now you explained it, even though it's not really relevant. Okay. Oh, yeah, good for you. Good for you. You learned about it. Yeah, good for you. But today we're going to talk about loopy variance from a different angle. The way we're going to talk about looping variance is more from like an executable looping variance point of view. Okay, well, we'll see. We'll give you some insight. Okay, so now this is just the general account for the loops. I don't need to read it. Okay, it's easy to follow. Okay, but loops are very hard to get right. Number one, you might run into infinite loop. For example, some of you got infinite loop in your lab test or projects. Too bad. Or you might simply got terminating loops, but you simply don't have correct result. Okay. So now these are kind of the issues we would like to catch, right? Formally. Okay. But we're going to see exactly how. Okay. So now, so these are just the common errors. We don't. But I tell you what, especially the last one. How can you be sure after executing this particular fragment of loop, we can really establish the following post condition? That's something we'd like to teach you how to prove. Okay. If you refer to OSC2, the textbook, okay, there is I forgot which page. Let me see if I got any page. Yes. If you go to page 331, basically the author presented 4 different versions of doing binary search. All of them were published somewhere, but all of them are wrong. Okay, even though they were published. What's the point? The point is getting loop to work is actually not trivial, even for simplest example like a binary search. Okay, so now I just want to say we want to show you the technique so you can try to maybe do a little bit proof by yourself about loops. Okay, so now let's talk about first of all the syntax for the loops quickly. Okay, for the syntax, for those of you who are still not familiar with the from until, maybe you have been using across all over. That's okay. Let's get it right now. So you got a from, you have until, you have loop, you have end. Okay, and then you might start with some precondition before executing the loop. Upon the termination, you want to establish some post condition. Okay, and then the until over here is really the tricky bits, because that's different from how you will program in Java. Okay. Let's say this is your Java while loop, okay? I'm just trying to show all the correspondence. For example, if you say while, for example, x is larger than 0, I'm going to do something over here. So I call this condition over here the stay condition, in the sense that you stay in the loop and repeat the body of the loop as long as this condition is true. In IFO, the until condition over here is so-called exit condition. And that's exactly the opposite, or it's a logically negated, okay, from the state condition. So if I want to translate this loop over here to IFO, I would say from something until it is not the case, x larger than 0, right? And then you do the rest. Okay, so that means you can see that this is equivalent to x less than or equal to 0, right? So think about the two things are saying the same thing. Over here, we're saying that you're going to repeat the body of the loop as long as x is strictly larger than 0. And here, we're saying that we're going to exit from the loop as soon as x becomes not positive. Both things are equivalents. Okay, but for the purpose of the exam, you want to get used to using exit condition as opposed to stay condition, although they're interchangeable if you do the logical negation. Any questions just about the syntax? Okay, so now that's about the syntax. In order to prove the correctness of the loops, we have to introduce you contracts for loops. So there are two kinds of contract for the loop. One is called loop invariants that you were introduced to. Did he talk about loop variance? You think so? Okay. Anyway, there are two things. There are two kinds of contract you have to know for the loop. One is called loop invariants and loop variance. Okay, we'll get to them. Okay, so these are the two loops. Okay, state condition, exit condition. Okay, exactly what I just said. Okay. So now what we want to introduce is the syntax for loops, contracts. So we have from, and then we have something called invariance. The same keyword as for the class invariant, the same. Okay? Invariance, let me just mention all the things and then we'll talk about it. Well, I'll show you the simplest example to understand everything. We got invariance, and under the invariant, it's almost like a pre or post condition. You can put a tag, and also you can put some Boolean expression. Okay? And also, you got an exit condition until. You also get the body of the loop. And now we have another keyword called variance. And then after that, we also got, and that's it. That's a complete syntax for the loop in order for proofs. A very quick summary for the fundamental difference between invariance and variance. Invariance literally simply means the Boolean expression should remain true throughout the execution. It doesn't change, always true. On the other hand, for the variance, it must change between iterations. It must change. That's kind of the interesting bit. And one more thing, invariance is always a Boolean expression. Okay, either true or false. Variance, for our purpose, is always an integer expression. Okay, and that integer value should always change between the iterations. More precisely, if we start with a variant value, let's say 10, it should strictly decrease between iterations until it gets to 0, something like that. Okay? But let's see one example. Any questions? Yes. For loop, well, you can think about, well, let me just say this. The question was, what about for loop? For loop in Java is like a while loop, right? Similar. So if you think about a for loop, it will be for, some initialization here, and then we got not B. Okay? And that will be the body of the loop. It's similar. However, the condition you put in for loop is just the same as a while loop. They are state condition. They are not exit condition. Okay? So again, you want to really be aware. Whatever you put in IFO until is an exit condition. Okay? Which means as soon as it is true, you're going to exit rather than staying. Okay? Okay, let's now talk about loop invariance and loop variance. Okay? Let me just describe to you just by using the flow chart. Okay? Quickly. You saw something similar, right, in the beginning of the course when I talk about how the runtime assertion checking will work. Okay, I want to do something similar. I'll just show you the abstract ideas, and then I'll use one example. Okay. So now let's think it this way. First of all, you have some initialization part. Okay, just called inits. Execute it only once. Once you execute this, okay, you have to make sure you establish the loopy variance. The loopy variance must be established even before you enter the loop for the first time. Okay? So now, if after the initialization of the loop, if the invariant is not satisfied, you got a loopy variance violation right away. We'll see how. Okay? And then you will check to see if the invariant is simply satisfied, then we'll go ahead and check to see the exit condition. So why? Why do we check the exit condition right away? Yeah, because in some cases, you may not even want to enter the loop. Sometimes, right? You may just bypass the loop body for the first time even. Okay, we'll see example. Okay, so now you want to check the exit condition. If the exit condition is simply just true, you will simply exit from the loop like this, right? Just exit. Otherwise, if the exit condition is simply not true, that means I want to stay, right? If I want to stay, I will simply stay here and then execute the body of the loop. Okay. At the end of the iteration, I have to evaluate the variant expression over here, loop variance. And then if the variance is strictly less than 0, I will get a loop variance violation. If it is larger than or equal to 0, I'm okay. Okay. And then after, let's say if there's no variance violation, so which means V is, you'll see here. If the variance is larger than or equal to 0, I will go back to the beginning of the loop, but now I'm not going to execute this one more time, no. I'm simply just going to check the invariance. Okay? So that means after the first iteration, is a loopy variance still maintained? Okay? So now, one more thing to say, and then before I show you one example. After the initialization, the loopy variance is simply established. Okay? Established. And then after every iteration of the loop, you want to make sure when you come back to the beginning of the loop, you want to make sure the invariant is maintained. Okay, it's actually very useful for you to prove the correctness of the loop. Any question just about abstractly speaking, how these things work together? Okay, right? Let's try one example. Okay, so now this one is as easy as I can make, really the easiest one. Okay, so now the same diagram over here. Okay, is it visible from the back? Good. Now, let's say we try this particular loop. We simply say I is simply assigned to 1. I is simply assigned to 1. Okay, and now the invariance is exactly over here. Let's see that's invariance. We want to make sure this invariant is first established. Is it established? Yes, because 1 is indeed between 1 and 6. Okay, we are good. Okay, and then now we check the exit condition over here. Is it true or false? False, right? Because you see 1 larger than 5 is going to be false. Okay, so that means we'll go into the loop over here, and that will simply tell us iteration 1. Okay, and then we're going to increment I from 1 to 2, right? And then once you increment it, what about the variance? It's going to be 6 minus 2, right? Because I has been incremented from 1 to 2. Okay, that will simply just be 4. And 4 is not less than 0, so we don't have the loop variance violation, right? So we'll simply go back. That's the first iteration. So after the first iteration, iteration 1, what about the value for I, right? The value for I after the first iteration is simply just 2. Okay? So now let's try a little bit more. So now the value for I is simply just 2. What should we do now? Check the looping variance, yes. In that case, 2 is still within 1 and 6, right? Let me use a different color. So now in this case, 2 is still within 1 and 6, so we are good. Okay? So now looping variant is again satisfied. And then we're going to check the exit condition. Is it true or false? False, very good, because 2 larger than 5 is going to be false. So we're going to go there, and then we say iteration, print it out, iteration 2. Okay, and then the pattern goes on. I have a question for you. According to this setup over here, how many lines of printout are we going to have? 5? Are you sure? Iteration 1, iteration 2. 6. Really? Well, you shouldn't change your answer when I question you, right? Well, let me ask again. How many times are we going to print out this particular line? 4 is a new answer. Interesting. Okay. I heard 5. Well, guys, it's not hard, right? 5? Okay, everybody agree? Anyone disagree? 5, actually. Okay. You're going to get iteration 1, 2, 3, 4, and 5. Okay, and another question here. Let me fix this to be a little bit over. Okay. After we printed out iteration 5, in the 5th iteration, I would be incremented from 5 to 6. Agree? Okay. So that means I would become 6. And then so now since we are in the final iteration, after the final iteration, now when we go back to check the invariance again, is the invariant going to be okay? Okay, still. So that means upon the termination of your loop, your invariant must still be maintained. Okay, so 6 is okay. Okay, that's good. Now, what about exit condition? 6 larger than 5? True. That means time to exit. So you can see upon the termination. Oh, one more thing. What about loop variance? 6 minus 6, right? 6 minus 6 will just be 0. Upon the termination, invariance is satisfied, and the variance over here is simply larger than or equal to 0. Okay? Think about it a little bit. It's a little bit tricky. Are we okay? Before I ask you some questions. Yes? No. So you can think about the invariance or variance. Sorry, are you talking about, let me make sure. You mean invariance? Variance, okay, sure. Okay. The question was the variance checked upon termination? The answer is no. Because you can see the diagram here, as soon as the exit condition is true, we simply just exit. You only check the variance within the iteration. At the end of the first, at the end of the second, at the end of the 5th. Only 5 times. Okay. Okay, so now I have a question for you. What's going to happen if, let's do something, let's go one by one, okay? Maybe I want to make a copy of this. Okay, so now I propose the following change. What if I change that to 5? Anything? Are we still gonna get some printouts, or we're gonna get some violation? When exactly? Yeah, exactly, right? So now, if we change it to 5, that means we're gonna get loop invariance violation, because after the 5th iteration, I becomes 6, right, as we explained. In which case, it's not going to be okay. Are we okay for this? Okay. Let's do another one. We're going to see a little bit more complex looping variant in just a moment, but let's do this one first. Okay, let's do another change. It'll be problematic. How? Yep, in the final iteration, okay, let's say at the 5th iteration, we know that I becomes 6, right? Now, if you try to evaluate this particular variant expression over here, 5 minus 6 becomes minus 1. Okay? So, it's going to be loop variance violation. Okay, just a very quick change for you. So what does that mean? That means you're going to be very careful when you specify the looping variance and variance. In the exam, it could be that we simply leave the looping variance or variance empty and ask you to specify the correct ones. Or we give you the wrong ones and then ask you to explain if there's any error. Okay, either way, and fix it. Any questions about this? We're okay, right? Okay, that's good. Okay, that's about the contract for loops. Invariant is simply just a Boolean expression. Okay, invariant has nothing to do with the termination, nothing to do with that. Okay. Okay, so now let's say this. For the looping variant, it's really hard to give you a very detailed lesson. I'll just try to go by examples. You can think about the best practice for writing the best practice to write a looping variant that's easier for you to conduct the proof is to make your looping variant very similar to the post condition. Okay, what does that mean? Okay, let's say this. Let's say we want to calculate the maximum of an array. That's a post condition. Whatever result you return is going to be the maximum of the array. So that means we're going to scan the array from the left to the right, right? Well, what will be the looping variance in this case? Conceptually. Somehow you can think about, let's say this is the input array you have. Let's say this is the input, which can be arbitrarily large. You know that the post condition tells you whatever result I get is going to be the maximum as far as the entire array is concerned. Agree? That's a post condition, conceptually. How about looping variance? I basically want to specify the looping variant in a way that depends on the progress we have made so far. Okay? So now what does that mean? So now for the looping variance, we want to say maybe you have a loop counter I. I might be pointing to here. We want to say whatever result you get so far is the maximum over the array we have scanned so far. Yeah, questions? Answer. Oh, no, I just want to explain quickly. Yeah, well, we can see the answer for sure. Yeah, I just want to make sure everybody can follow this intuition. Well, for the exam, you only have to know about simple ones. For let's say over an array, and the most common pattern for looping variant over an array is to say based on what we have scanned through the array so far, that's the result we have got. Okay, so every time when we make some progress by increasing I to maybe I plus 1, that means we are growing the search space. Eventually, we want to make sure everything has been scanned through in the array so that the looping variant will just be equivalent to the post condition. Okay, that's kind of the intuition. Okay, but we're going to see exactly how to do this. Okay, let's now go for, okay, result is the maximum of the part of the array so far. Okay, but how exactly do we translate that into executable code or design? Okay, that's the question. Okay, and then you want to make sure looping variant is established before the very first iteration, as we said, and also is maintained true between the iterations. And for the variant, it should be an integer expression, okay, and then somehow the variance can tell you exactly how close you are. The closer you are to 0, the closer you are to termination. That's kind of intuition. Maybe you start with the variant being 5. That means you got maximum 5 iterations because you guarantee every time when you finish a particular iteration, the variant expression will decrease its value. 5 to 4, 4 to 3, 3 to 2, 2 to 1, 1 to 0. And then you cannot decrease any further. Okay? Okay, so now, well, something you can read. As soon as the loop variance becomes 0, it must be the point that the exit condition becomes true. If when the exit condition becomes true, but your loop variance becomes negative, well, in that case, of course, you got trouble. Right? Okay. All right. Now, what I want to do is to do some example for you. More example. Let me just explain one more diagram. Oh, by the way, these are the three things I just talked about. The three fixes. Okay, I just use a different page to explain. Okay. So now this is just another diagram. It's actually quite nice because it corresponds quite nicely to how we view each predicate as a set of satisfying state values, right? If you think about it, I'll just explain this diagrams on the slides. You can think about as soon as you try to execute the initialization for your loop, you're going to enter a very big region over there that is going to satisfy the loop invariance. Okay, that's a loop invariance. You want to make sure, starting from the first iteration until the last iteration, you're always within this boundary for the loop invariance. It's always there. Okay? Now, as soon as your state enters another region where the exit condition, which is just another Boolean condition, right? As soon as you can see the intersection between the loop invariance and the exit condition. When both are just true, that means it's time to exit from the loop. And what do we expect to see? As soon as you terminate from the loop, you want to make sure the post condition is also satisfied. Right? So this is one state where you can see this is also the case where post condition is also satisfied. Okay, there's a little bit more conceptual picture to show you. Okay? Did Jeff show something like this? No? Oh, okay. Anyway, yeah. It's quite a nice diagram, okay, if that makes sense to you. Okay, let's see a little bit more example. Okay? Yes. Which line? Oh, the dash. Yes, yes. You can think about over here. So this is initialization, right? This is the first iteration, second iteration, as many iterations as you like, as long as it's a finite number of iterations. And then this is the last iteration. And the last iteration should bring you to a state that is going to satisfy both the loop invariance, exit condition, means it's now time to exit, and also establish the post condition. Okay? Yeah. That's what it means. All right, let's now do more example here. How about start with this? What I would like to do is to ask you, readable, right? Let me explain the context to you, and then I'll ask you. We are trying to do this feature here. It's a query. So we have find max. We want to find out the maximum in the array. We give it an array of integer. Okay, maybe a pen would be better. So we have an array of integer being the input. We want to return the integer, the maximum. Okay? And then we simply say loop counter initialized to be a lower, and then we assign the result to be the first elements of the array. Okay? And then we have some loop invariants over here. I'll go through the loop invariant in just one moment. Okay? And we say that we're going to stay there as long as, we're going to exit from the loop as soon as I is strictly larger than a upper, right? I can tell you that the exit condition is correct. And then inside the loop, we're going to say if the current element we are looking at is strictly larger than the result, that means we're going to update the maximum, right? Well, very standard way of doing things. And then make sure you do this one as well to update the loop counter. And this is the variance expression over here. Okay? And then we want to make sure at the end of the loop, we have this particular predicate. So now let's focus on these. I want you to look at, first of all, this expression over here, and also this expression over here. The first blue one is the loop invariance. The second blue one is the post condition. This corresponds to what I said as a best practice in order for a proof. You can see that over here, the loop invariants look very similar to the post condition. Tell me syntactically, where is the difference? Yes? Upper limits, yes. You can see over here is I. And over here it is a the upper. Intuitively, you can think about exactly the diagram I just talked about. You can think about each iteration is going to be just I over here. We want to increase the I until we reach the last part. Once we reach the last part and exit from the loop, then we're done, right? Okay, good. And I've got a question for you. Is the loop invariant going to be okay? Well, think about the pattern of my teaching, right? If I ask you something, yes, good, you're right, that's wrong. Good man, that's wrong. Why? You don't know, okay. Well, also, since I'm highlighting these two things, right, that means they are wrong. Okay, I can tell you that the post condition is okay. Post condition is quite straightforward. From eta lower until eta upper, okay, we're saying that result must be larger than or equal to every element. I can tell you that this is 100% correct. However, the loop invariance is not correct. Somehow, we'll run into loop invariance violation. Can you see how? I'll definitely trace together with you. I want to see if you can imagine a little bit. If you can see any loop invariant violation, tell me which iteration you will get. Think about it, think about it. It's quite interesting to actually go over this wrong version. Number one, it's very common. Number two, it's really nice to go over each iteration. You'll see different insight into the predicates, right? You'll be, you got some answer? How about try you first, and then you later, yeah. Nothing to do bounds, I can tell you. Nothing to do with bounds. We don't have any array index out of bounds exception or violation. No, that's not the case. So I tell you what, yeah, nothing to do with that. Want to say something or similar? Ah, okay. How about we trace it together? Okay? I can tell you that there's something wrong with this. Oh, sorry, not this one. Sorry. This one here. Something wrong with this value here. Something. That's exactly how it is wrong. The best way to see this, first of all, would you be feeling comfortable if I refer you to this particular expression? I say for every j, eta lower less than or equal to j, less than or equal to I, and the result larger than or equal to aj. Are you comfortable with it? No? Okay. Really? Okay, well, if you're not, then I gotta explain, right? Okay, this is loop invariance. For every j, you know what this for every is, right? Okay, good. Such that eta lower less than or equal to j, less than or equal to I. What does that mean? That means j can be any value you choose between eta lower and I. For example, if I is simply, let's say eta lower is 1, and I is 5, for example, then j can be 1, 2, 3, 4, 5. Okay? It is the case over here, result is larger than or equal to aj. Okay? We're saying that for every value for j, this particular Boolean expression should be true. Okay? Just that'll be enough just for now. Let's be evaluated together. Okay? So now, given that you are very comfortable with this particular flowchart over here, right? Let's try for this loop invariance here. So now, we know that initially, let's think about the value. The value for I, okay, just focus on the value for I. What's the initial value for I? Eta lower, and we assume for all the array, eta lower is 1, okay? I is simply just 1. And now result is simply ai, okay? So now I is simply just 1, so which is pointing to the first element, right? Or let's say we talk about this particular rate. Let's say 20, 10, 40, 30, okay? We want to find out the maximum. And then AI would just be 20. Agree? Okay? So now that means the result will just be 20 at the moment. Agree? So now, let's see in the beginning. When we evaluate invariant for the first time, what's going to happen? We're going to have for every j such that eta lower, which is always 1, less than or equal to j, less than or equal to I, which is 1. Agree? It is the case. Result is 20, right? 20 larger than or equal to aj. Is this universal quantification true or not in the beginning? Well, hopefully you can see, right? So now, how many possible values are there for j? Just one, right? The only instantiation you have is simply 20 larger than or equal to a, 1. 20 larger than or equal to that is true. Okay, no problem. Okay? And this actually corresponds to the first row. Okay, you can look at the table. Okay, yeah. Let's see the second one. I'm going to use a different color. So now we know that after this, we're going to increment the value for I into 2. Okay, so now a question for you. For the very first iteration over here, are we going to modify the value for result? Because for the very first iteration, we can see we start with a dot lower, right? We start with a dot lower, being I. And now for the very first iteration, what's ai? Just 20. Agree? 20, and result was initially to be just 20. Comparing itself, so there's no need for updates. So the maximum remained to be 20. Okay, that's the first iteration. Okay, so now that means the maximum remained to be 20. Okay, after the first iteration, and now I has been incremented from 1 to 2. You haven't lost yet, have you? I hope not. Okay, so now for that, what should we check over here? We should check to say for every j, such that 1 less than or equal to j less than or equal to the value for I, which is 2. And then the maximum hasn't really changed yet. 20 larger than or equal to aj. Is this universal quantification true? How many j should we consider? 2, right? 1 and 2. So basically, we're going to consider 20 larger than or equal to a1, and also 20 larger than or equal to a2. Yep, that's fine. And notice one thing. We are actually considering a2 over here, even though the body of the loop hasn't really considered that. That's a very important insight. I repeat. Over here, the loopy variant tells us the current maximum 20 is larger than or equal to a2. a2 is over here. However, the body of the loop have only considered up to here only, but we haven't really reached this part yet. That's the problem. But we are lucky, we haven't got to that yet. Now, third iteration. There we go. That's what we're going to see. What about the third iteration? If we go for the third iteration, I'll put it here, the I value and also the result. We know that the I value currently is simply just 2, right? That means we're going to look into this particular value over here. Okay, is 10 larger than 20? No, right? So that means we don't update the maximum, right? So that means the result remains to be 20, and I will be incremented from 2 to 3. Okay, so now here comes the problem. Okay, at the end of the third iteration, what kind of loopy variance should we evaluate? I'll write it down. It's going to be for every j such that 1 less than or equal to j less than or equal to I, which is 3. And then 20 larger than or equal to aj. And now you tell me whether this universal quantification will be true or not. How come? Yeah. We know that we're going to consider j being 1, 2, and 3, right? 1 and 2 is fine. However, when j is 3, 20 larger than or equal to a, 3. Again, this is 40. Now we're not lucky this time. 40, we haven't considered that yet, but loopy variant asks us to consider that. Okay? And this is false. This is where you got looping variance violation. Guys, I know this one is a little bit tricky here, but I think it's actually even more important for you to get this one right to understand before I show you the correct version. So what's really the problem for this wrong looping variance? The insight is over here, the I over here that we are trying to, the looping variance I is only to be considered in the coming iteration. That's a problem. It's not really the I you have considered already. It's the I that's to be considered. Okay, having given this, how do we fix it? I minus 1. Oh, that's smart. Yes, exactly. Yeah, that's exactly how you fix it. Yeah. Wow, seriously, that's it. Correct version is I minus 1. Yeah. If you simply want to hack the loop invariant, you're lucky. You hack the right version. Okay. But now, I want to explain to you. Well, I don't need to go through everything here. Okay. I just want to go through the very first one. Okay. That's the correct version of the loop invariance. Okay. It's not going to have the same problem as we said previously. But now I want to ask you just one question here. Okay. As follows. Let's say we do the same initialization. So that means I would just be initialized to be 1. Okay? And result is going to be AI, which is 20. Good. So now, when we try to check this loop invariance over here, okay, what exactly are we checking? I'll write it down. You can think in this way. Either you can think about it's I minus 1, or you can see it's strictly less than I. Either way, okay? Either way will work. But if you want to put in I for syntax, you got to say I minus 1, okay? Let me write it down. So you have for every j such that a dot lower is simply just 1. Less than or equal to j, strictly less than 1, or less than or equal to 0, right? Either way, okay? Such that it is the case. Result, which is 20. Larger than or equal to aj. Okay, this is the first time you want to check to see if the loop invariant is established, even before the body of the loop is executed for the first time. Now, I have a question for you. Is this going to be true or false? True, false, true, false, or depends. It doesn't even check. What do you mean it doesn't even check? Yes. Yeah, it's empty range, right? Yeah, exactly right. Okay. Wow. Okay. Actually, I think that we briefly talked about this in one of the previous lecture, where we talk about like a contract. That may be the part you want to review. Basically, you can think about if you only look at this predicate over here. Is there ever going to be a number that's going to be larger than or equal to 1, but less than or equal to 0? No. Okay? So this range is basically equivalent to false. Okay? So now, if you recall what you learned in 1090, for every x such that you got false range over here, right? And some predicate of x. This is always true for a very simple reason, okay? Because you remember for every x, if you got some range predicates and also predicates, right? We know that this is equivalent to for every x, and then Rx implies Px, right? So now because the range is simply false, false implies anything, so that would be true. Okay. Well, I assume you knew that from 1090, right? I hope. Okay. Well, you got about a week to review 1090 if you don't feel comfortable. If you don't have other things to do. Okay. Anyway, any question about this fix over here? Yes. For the wrong version. Okay. Which one? Oh yeah, exactly. Yeah, exactly. So. Oh yeah, I tell you what, in the wrong version, you don't even get to that point. Because in the wrong version, you already got a loop invariant violation.
Well, for that example.
For that example, yes. But since you talk about that example there, you got a loop invariant first. You got a loop invariant violation first before you get to that array index out of bound. Okay, yeah. Okay, guys, his question was, isn't that true that at the end of the final iteration, the value for I would just be a dot upper plus 1. In which case, if you try to evaluate over here, you will get array index out of bound exception. It is true. However, logically, it doesn't make sense because according to what we just argued previously, you will already get a looping variance violation after the second iteration. You get it first before you get to array index out of bound exception. Okay? Think about it when you review the lecture. Yeah. Wow. Okay. Let's go a little bit faster. Okay, but I think I covered already the most complicated part. Okay, let me just go use about 5 to 10 minutes to finish the parts, and then I'll have 10 minutes to do agents. How about that? Quickly. Okay. If not, I tell you what, if I really cannot finish the agent part, don't worry, I will have a review section next week. Okay. Yeah. Eventually, you will learn. Somehow, this winter has been much harsher than last winter. You see, last winter we got strike. And this winter we got so much freezing rain and snowstorm. Yeah, it's too bad. Yeah. What's going to happen next winter? Yeah. All right, so this is the correct version. Okay, I do have one more thing to ask you about. Okay, if you try to see the second example in the slides, basically I changed the loop variance to be a dot upper minus I as opposed to plus 1. Okay, as you try to trace through the code, it's going to run into loop variance violation. Okay, so that's something I will leave to you. Okay, if you really got trouble, ask me during the review lecture. I can go through. Okay, but I think based on what we learned about the flow chart and also the simple example, you can easily trace to see how this happened. Okay. Okay, after this, we're going to talk about how you can prove the correctness of loops. Okay, by the way, this is the final correct version. The final correct version is, for the looping variance, you're going to say I minus 1. Okay? And for the loop variance, you're going to say a dot upper minus I plus 1. That's the final correct version. In the previous two versions, I just give you one wrong, each one. Either looping variance wrong or the loop variance wrong. Okay, everything you can see. Okay, some exercise for you. You can think about it, okay? Basically, I'll just give you another example. So here we have, basically, let's say we have a dictionary class. We got values, we got the keys. Actually, very similar to what you did for the birthday book, similar, okay? And then let's say we have one get keys feature, okay, queries. And then we simply want to return, given a value, we want to return all the keys, like a remind feature in the birthday book, similar. Okay? So now I want you to think about it. How would you specify the loop invariance over here? Think about it. Okay? If you want to ask me more about the answer, we can talk about it next week during the review. But it's better for you to think about it first. It's doable. Okay? Huh? Which one? Get keys, given a value, you want to return all the keys associated with the value. It's like given the birthday, you want to see all the people who were born on that date. Yeah. Okay, so now let's do a little bit more. Okay, now how do we prove correctness for the loops? Okay, how do we do that? So now I just want to go over with you quickly the proof obligation. If you want to prove the correctness of the loops, there are several things you have to prove. Okay, I kind of put the English version over there to give you some intuition. And what you have to remember, what you want to put on your data sheets, the rule. Okay, let's say this is what you're given for the loop. You have some starting precondition, you have some post condition to establish. You got initialization, you got loop invariance. You got exit condition, you got the body of the loop, you got loop variance. Okay? So you got in total 1, 2, 3, 4, 5. 5 correctness conditions to prove. 5 for the loops. Okay? Let's do one by one. Let's first talk about termination. How about that? Termination. Termination has to do with the loop variance. Okay, so now you want to make sure the loop variance is always non-negative. That's something you want to make sure. Okay? You want to make sure never ever loop variance will actually get decreased into 0. Or more precisely, you want to make sure the body of the loop is actually going to make sure is going to establish that v is larger than or equal to 0. You can think about this as more like a post condition for every iteration. Okay? Now, how do you formulate it? As a Hoare triple. Well, if you think about the Hoare triple, you will know that at the end, oh, good. Okay, that's a post condition here, right? V larger than or equal to 0. And then you want, okay, I'm going to show you the whole thing. That's what you have to prove. Okay? I'll read it to you. You can see the Hoare triple here. We want to say you're going to execute the body of the loop. You want to make sure at the end, v is larger than or equal to 0, right? What can you assume? You can assume that loopy variance is the case, and also we have not exit just yet. Okay, that's, yeah. Okay, let's do another one. What about over here? This one's interesting. You want to make sure after every iteration, you decrease the value for loop variance. So now in this case, what should be the post condition we're trying to prove? Yes. Correct. That's exactly correct. So you had to use an old expression over here. Okay, v exactly less than v0. Okay, that's exactly what you will get. Okay, just like that. Okay, can we do the rest very quickly? Okay, and then I really have to go to agents. Okay. So now let's see this. So now this, excuse me, this part is really about the termination. Okay, the termination part for the proof. What about the partial correctness part, which means that we assume it is going to terminate. Okay, so now let's see this. Given the precondition Q, we establish the looping variance. This one's easy. How? Well, are you convinced if I say that? Okay, yeah. Given the precondition, you try to execute the initialization part, and then it's going to establish the looping variant for the first time. Okay? Okay, good. Now what about this part? We are saying that not only that it's established, but also it's maintained. We want to make sure at the end of the body of the loop, if we are not yet ready to exit, we're going to maintain the looping variance. So now, what should we do? Something similar. You can see that we assume that, first of all, looping variance was true previously, before the iteration, right? At the end of the iteration, looping variance is also maintained. And also you assume that we have not exit just yet. Okay, and then the body of the loop. Okay? Yeah. I don't think you should really memorize this. Okay, maybe put it on your data sheets. And then, but you should really know the intuition behind. So if we ask you a question about it, you will be able to answer. Okay? Finally, this is the most important one. Let's say we are ready to exit, and then the looping variant has been maintained. We want to make sure the post condition is really established. What about this one here? Yeah. B and I. Mm-hmm. With nothing in between, yes. In this case, because now we are done. No more body to be executed, right? I mean the loop body. Well, what we can do is no Hoare triple. This is the only one we don't need a Hoare triple. Just to say that implies a post condition. Okay, good. Yeah, so these are all the correctness proofs, condition you gotta prove. Okay, so now what I would like to do is I will finish this lecture, just this part here, in 2 minutes by going through the rest to tell you how to study for the slides. You can ask me during the review session if there's anything that's not clear. Okay, so now your exercise is to prove, okay. Number one, if you're given this particular fragment of code, You have some loopy variance, you have loop variance over here, right? Given the code. How do you formulate all the correctness condition we talk about? Number one, okay? So I do have a solution over here for you, okay, plugging in the exact equations. Do not look at this until you are comfortable of doing that yourself, okay? That's the first exercise. And the second exercise, prove all of them. If you can prove all of them, you are more than ready for this part of the course, for the exam. Okay? The most difficult part to prove, the most difficult part is about how you can maintain the looping variance. That's number two. For that, I'll give you a solution. Okay? But give it a try at least. The exam might turn out to be easier than this, but I would say for your knowledge, you better try. Okay? You do have time. Okay, after this, yeah, as you go through, there are certain tips for doing the proof over here, just for your reference. Okay, you can go through them. Okay, any question just in general about the this lecture here? Are we okay? Okay, now you have choice. Either we can take a 5 minutes break and then do another 20 minutes, or I can do 20 minutes now. 20 minutes, right? Okay, how about we just do 20 minutes? Okay, different topic. Okay, okay. Let me tell you. So that's it. I will confirm with you the time for Tuesday and Thursday next week. But study the slides and then let me know if you want me to go through any other parts. Okay, at least I give you the clear big picture. So now, there is a particular slide you want to go through in the other section. I'll point to you exactly where. If you go to the course wiki. Okay, if you go there, again, you can just log in first. Okay, let me log in first. And there's a particular slide you should really go over. Okay. If you go under SVN slides, and then you gotta type. Okay. So now under slides, so go to just this particular slides called. Let me see, tuples and agents. Okay, number 15. Just go to that one. Okay, that one there actually has several examples using the agents. That's something both sections are expected to know. Okay, but what I will do is I will just choose one of them, the most complicated one, to show you in Apple Studio to give you the insight. Okay, let me use hopefully 15 or 20 minutes at least to give you some idea. Okay, so now what I want to go to is this particular example. You can, so just some basic knowledge about the tuples, right? That's something you can go through. The one I would like to go through together with you, I also will do some example. I also post the source code on the web, so you can go through them. This is one I would like to go through with you. Okay, this one here. Counting quantifier. Okay, something to do with logic, something to do. Okay, let me just show to you, mathematically speaking. Basically, we want to implement this particular operator. Okay, your so-called counting quantifier. Counting quantifier. For example, let's see some example over here. Basically, let's say you have over here. Can we just have a look at this particular example over here? Okay. You're trying to apply the counting quantifier over here over a range of numbers. You can say I is in between 1 and 6, for example, right? So that means we can consider 6 values of I. We're going to consider 1, 2, 3, 4, 5, and 6. Okay? So now, this is the part that's critical. We want to say for every member we have in the collection, and when we implement, we're going to use an array, okay, for every number. We're going to say whether I is larger than or equal to 5 or not. For example, 1 larger than or equal to 5, 2, 3, 4, 5, and 6. Okay? Basically, all of them we're going to apply the same predicates, except that I is more like a placeholder. I will be replaced by every member you can draw from this particular collection, like an array. Okay? So now, and then we want to see exactly how many expressions will be evaluated true. That's why it's called counting quantifier. For example, you can see the first one, 1 larger than or equal to 5 is false. False. Let me write it down again. 1 larger than or equal to 5, 2, 3, 4, 5, and 6. Okay? So now, how many do we have? That we have true. 2, right? Only these 2. That's why the answer should be just 2. Okay, first of all, mathematically, let's understand what's going on here. And now, let me give you another example. Let's say counting quantifier, I would say number over here. Let's say I is between 1 to 100. Okay? In this case, I modulo 2 is equal to 0, which means I is an even number. What should be the answer for that? Well, 50, right? Okay, that's easy. Basically, you can, let's compare this example here and this example here. Okay? This part here is the range that we're going to use. In this case, we can simply use an array to implement. And this part over here is the interesting part. That part there is simply just going to take whatever I you have for the moment, which is just one single integer. And then the whole thing is going to apply certain expression like a Boolean predicates. In this example here, it's checking to see whether or not I modulo 2 will be equal to 0. In this example here, it checks to see whether or not I larger than or equal to 5. Right? So that means you can pass different function to the counting quantifier. How do you pass function? How do you use, what's the pointer to function notation we talk about? Agent, right? So we're going to use agent here. Basically, we are being very flexible over here. The range part can be any array of any arbitrary size. And this part for the predicates can be any Boolean function that's going to take a one integer and return a Boolean. Okay? Just get the big picture right, and then I'll do some coding for you. Are we okay? Okay, let me spend 15 minutes, okay? Then we're done. Okay, let me just go to iPhone Studio over here. Okay, I already started with something. Okay, I'll still do some from scratch. Let's do something that's fun, first of all. Okay, let me just say I do have something here for me to look at. Okay. Okay, so now let me define some queries over here. Okay. Is it readable? It's okay, right? Yeah, sorry, it's a bit small, but if you look at that should be. Oh yeah, you're right. Thank you. Good man. Good. Okay, good. So now let's see. Let's do one feature here. Let's say I do subtract. Okay, now it's well, I want to make it so dumb so it's easier to understand, right? So now let's say integer y integer returns an integer. Do result is assigned to x minus y, and you should have no question about this, right? Do I need to explain why this works? Really? Oh, no, I don't want to. No. Are you kidding me? Yeah. Oh, no precondition. Yeah, in this case, anyway, it will work. Okay, now I'm going to do something fun together with you, okay? I'm going to make sure I follow that, otherwise I'll go off the line too much. Let's do a test, okay? A Boolean test. Okay, so now what I will do is, let me just put a comment here. Okay, so I will call this partial application. Any one of you did a programming language called Lisp, functional language. You know what? It used to be in the curriculum, but they canceled that. It's too bad. Otherwise, it would be easier for me to teach. Anyways, that's not your fault. Okay, so now, let me say this. I have a question for you. Let's say I want to do local over here. I want to declare some variable f to be of type, some certain type. And now, if I simply say, oh, let's say f1, sorry, I meant to say f1. f1 is simply assigned to, I'll put agent over here. Okay, agent is a function pointer, right? So now I'm going to use subtract over here. Like that. So far, so good? So now, how many arguments am I supposed to take? 2, right? There's an interesting syntax you can use. Let's say I don't know what x should be at the moment, because I want to delay the execution. Put question mark. I can also put another question mark over here to say, I do want to store a pointer to this subtract function. However, I am going to leave the first and second argument flexible at the moment. It's called open arguments. Okay? Okay, so now, take a guess. Of course, it wouldn't compile because I haven't specified the type yet for f1. What should be the type for f1? Well, it's a common misconception. You thought it would be integer simply because you thought subtract would just return integer, right? But don't forget we say agent here. That means what we are storing over here is not really the return value. What we are storing is the pointer to that particular function, right? So what you will get is the follows. It's basically a function. Function is like a procedure that we talk about in the event-driven design lecture. Okay, function means something that will return something else, right? So now we're going to take a function over here, and then this particular function, because at the moment we simply don't know what we're going to take for the first and the second. So it's simply going to say integer, the first arguments, second arguments, and the return type. Okay? Okay, now here comes the funny part. So now let's take a look. Everything compiles. So now I want to, well, remember we can store this particular function using agents. Now let's say we want to call that, okay? Call the delayed function reference. Okay, now let me now really get an integer for you. Now if I say value is assigned to f1, f1 is not a function, it's a pointer to some function, right? So now I can specify what these two values should be. Okay, I can say f1 is simply 2 and 3. So now what should be value? -1 is quite obvious, right? Okay, I can tell you it's -1. Okay, let's do that first, and then I'll give you another interesting bit. Its value is simply -1. Oh, sorry. Okay, so now to really make sure everything works, okay, agents and T1. Okay, and then I'm going to run it. Oh, good. Okay, everything passed. Let me try another one for you. You can see over here we simply leave both arguments actually open, which means we are expected to pass, but we call that. Let me try another one. Let me say this. F2. F3. So now I'm going to say F2 is simply assigned to agents over here, subtract. I'm going to say for the first one, I don't know. I'll put a second one here. Which means the first one is like a don't note, but the second one is always 3. Okay? And then we also get F3 over here, agents, subtract. And now the first one should be 3. And the second one, I don't know. Okay, now let's compare F2 and F3. Basically, what are they similar? They are similar in the following sense. They are similar in that we are basically trying to make some partial application of the function subtract. For F2, we are trying to say the second argument is always going to be 3. Whoever is going to call this function later, they have no control over the second arguments. Okay, I'm going to write it down. Okay, whoever calls this function later has no control over 3, the second arguments. Okay. Similarly, whoever is going to call F3 later, they have no control over the first arguments, which is 3. Okay, let's see one example here. You will see immediately what I meant. Let's say we got value, let's say value 1, value 2, value 3. Okay, so now I would say value is assigned to F1 or F2, and then because F2, thank you, yes, thank you too, thank you. Value 1, thank you so much. Wow, you guys are good. That's good. Result, okay, I can say check result n, right? Yeah, I know. Okay, so now no, let me finish this first, okay? So I got value 1, I got value 2. Okay. And now what should I pass? Let's say how many arguments am I expecting to pass? Just, well, remember F2, we already fixed the second argument, right? So I'm only going to pass 4 over here. Okay? And now over here, value 3 is assigned to F3 over here. I'll pass 4 as well, which in 4 will be replacing this particular question mark. Okay? Basically, you can see this. This line here is saying that I'm going to store a reference to the function with a delay execution. However, I wouldn't tell you what the first argument is. I'm going to decide later. Whereas the second argument is already decided. Okay? So now what should be the type? Oh, maybe that's what you meant, just right? Now function over here, now you want to say for F2, because the second argument is already fixed. Oh, sorry, for function for F2, the second argument is already fixed. So we don't expect to take 2 integers anymore, just 1. That's why we say take 1 integer and return 1 integer. For F3 as well. Okay, you're going to take 1 integer and also return another integer. Okay, okay. Oh, maybe that's what you were talking about, right? Thank you. Okay, so now, good. Let's now think about what the result should be. Result is, let's say value 2 is, what should that be? 1? Well, because exactly, because 4 is going to replace the question mark, so 4 minus 3. What about here? Minus 1? Well, because we know that 4 is going to replace the second argument, which is y. Oh, so we got 3 minus 4. Okay, that's minus 1. I'm showing this to you because in order to use the counting quantifier, you do need this kind of stuff. Okay, that's why I'm showing you first. Okay. Okay. So now after this, let's write the test quickly. Okay, if I do that, I'm just going to get pass. Okay, let's get to the counting quantifier and then we're done. I do have some exercise on the file for you. We can do a little bit later. You can do a little bit later. Okay, so now how do we define the counting quantifier? Okay, so let's say this. I have over here, let's define another helper query. Okay, let's say we want to, so that one is just a warm-up, just for you to see how to use the agents. So what I would do is simple one.
let's say it's even. Okay, taking some integer, just 1 rather than 2. And then I want to know whether or not this integer is even number. So how do I tell? Modulo 2 would be 0, right? Result is assigned to I. Modulo 2 is equal to 0. Okay, just easy even, easy. Now I want to see exactly how later I can use agent to apply to this function here, and then somehow use a counting quantity to see how many numbers in the array is actually even. Okay, you can see everything work together. Let's see the counting quantifier quickly. Okay, I go to util class, utility. There's an exercise over here for you. You can, once you download the source code, try that exercise. Well, after this exercise, I can go over a solution with you next week. But after this, you'll be ready for this part of the exam. Okay. So now, how do we define a counting quantifier? Okay, you will see the solution also on the slides from the other section. But I want to just show you here. Okay, let's develop the code together. So let's call it counting. Okay, so now the counting quantifier, if you think about what we did before, what should you take? You should take, first of all, some range index, we're going to make it an array, and also pointer to some Boolean function. In this case, just take one single variable, okay, just the integer. That's exactly what we're going to do. Okay, so I will do over here a array of integer and also p predicates. It's going to be a function, we have just seen a function. And make it easy, it will just simply take integer as the arguments and also returns a Boolean. Okay? And then counting quantifier is simply just going to return some integer, right? Because if you have this, it simply tells you 2, right? It's integer. Okay? Let's pause a little bit. How would you implement this? You can think about what you're getting for the counting quantifier. You're getting an array, a collection. And number 2, you're given a pointer to some function. And the function is expecting to take an integer and also to return a Boolean. So how can we pass the input to the function? Basically, you have to go over the array that you're given. Go over the array, one element by one element. Each element is simply just an integer, right? Pass each element into the function for execution, right? Yeah, it's as if, it's pretty much similar like this. How do I evaluate this particular expression over here? Okay, I modulo 2 is assigned to 0. How do I evaluate this? You can think about this is the counting that we are trying to define. Okay, this is like an array of integers we are trying to go over, right? And then array, we can just use a cross loop to go over from 1, 2, 3, 4, all the way to the last one. But now this is certainly some predicates we have, right? You can think about the predicates like this. We don't know what the first one is, the I, modulo 2 equals 0. Now what should be these open arguments? It should be the first element in the array, second element in the array, third, all the way to the last element of the array. Okay, that's kind of the conceptual idea. Now, how do we do that? Let's do piece by piece. How do we go over the array? Across, maybe? Across A is, let's say, cursor. So now, we want to say every element in the array, we can simply say cursor.item. Right? How do we use that element there? We want to pass the elements as an input to the function. Right? It will be very intuitive for you to use the syntax. P is the pointer to the function, which is expecting an integer. Well, we simply just give that. Apply the function. What's the return value from P? Boolean over here, right? And basically, we want to say if the result is simply true from this, so we're going to say if applying this is going to give us true. And then we're simply just going to increment the result to 1 by 1.
Okay, like that. And everything should compile. Any questions? Yeah, we're almost done. Just give me another 3 or 4 minutes. Yes, question.
We're assuming we're going to the right P.
Oh, we're going to give the P right now. Yeah. So this is only about a supplier for the counting, right? We're going to see exactly how to use it. Okay. Again, let me just highlight again the critical thing over here. We are taking for the counting an array and also a pointer to some function. And the function must have the following argument type, which is integer, and the following return type, which is Boolean. Okay? Like that. Yes?
So there must be a return.
There must be a return type, yes, because it's a function. If you don't want any return, return type will be a procedure, like how we did in the event-driven programming, right? Okay, let's finish the last bits over here. So now I'm going to do another one, test util, over here. Okay, let me just do another test. If I say T2, okay, and then we're going to say comments, okay, T2, agents to named function. Here I say named function. Maybe in the review session, I'll show you some optional syntax, how you can create anonymous function, which means a function without a name, but that's optional. Okay, so now how do we do it? As easy as we can simply say this. Let's say local U is util, and also A is an array of integer. Okay, let's try this quickly. So now let's have A is assigned to, let's say 1, 2, 3, 4, 5. Let me have A1 and A2. How about that? A1 and A2. A1 is like that. So now how do I want to know how many numbers are there that's even in A1. I can simply say result is assigned to U dot counting. So now what should I pass? First of all, I should pass A1. Number 2, I should pass a reference to some function, which will take an integer and returns a Boolean. Well, I have. Okay? I can say, don't forget, you got to say agent over here. Okay? Agent, if you simply say is even without agent, that's not good. Okay? We want delay execution. Is even, and now I want to say for the first argument, I simply don't know at this point. What's going to happen is, if I leave this question mark over here, that means it's open. That means when I try to call later the counting, when I later try to call the counting over here, it's simply just going to use the cursor item, in which case it will be every element in the array. Okay, that's something you can go through. Okay, let me just compile. Okay, let's see what happened. Result is, oh, of course. And what does that return? Integer, right? If you try to call the counting, it's going to return an integer. Okay, it's simply just going to return an integer. Okay, integer here. Okay, equal to 2. Yeah, how many? Yeah, I know. How many integers do we have? Even numbers do we have? 2. Okay. Okay, let's see. Yeah, thank you. Okay, I think I'm getting there. The target, okay, so now I want to make sure void safety create U dot make. Okay, there we go. Okay, so now do you think the test should pass? Should, right? Let's double check. If I try that over here, good. Oh, I haven't added it. Yes, exactly. You don't want to get this kind of false hope. Okay, and then we have that. Okay, good. Let me do one more. Okay, we're almost there. Okay, so now let's try another one. Let's say I simply got A2 is assigned to. How about give me an array, anything. 2, 2, 2, 2, and then? That's it? Wow, everything's even? Are you sure? Wow, that's kind of fun. How about just empty array? No, U is already there. Yeah.
A2, thank you. Okay, so now what do you think that should pass? Should, right?
All right, you pass. Okay, so now this is the level of complexity you're supposed to know for the exam. I would suggest I'm going to make the source code available. Go over the code first, and then go over the slides. Ask me a question on Tuesday. That'll be the best way for you to study. Let me mention one final thing, okay? When you look at the source code, there is some exercise for you. Okay, over here. The exercise basically asks you to define another counting quantifier. Rather than taking one integer, he's going to take two integers. And we want to solve a problem like this. Let's say I'm given an array, let's say 1, 3, 4, and 2. I want to know how many pairs of numbers inside will add up to 5. How many? If you can see. 4, right? You got 1, 4, 4, 1, 3, 2, and 2, 3. That's something that can be solved by using counting 2. So that will be quite an interesting exercise for you. But if you can do that, try. Otherwise, I can go over a solution with you on review session. Okay, any question for me? Good.